Okay, this is a video on this triangle problem where we're writing a function to represent the area of the triangle formed as point P moves from B to C and then C to A. Okay, so let's first start with some given information here. We know that the distance from C to AB is 6 units. And now creates two special triangles on the right and on the left. So on the right, I've now got a 30, 60, 90 triangle. And opposite the 30, we know is 6. So opposite the 90, or the hypotenuse, is going to be double that, or 12. And then opposite, which is going to be the other angle, opposite the 60, is 6 root 3. Now let's look to the triangle on the left. Opposite the 45, I'm going to have a 45, 45, 90 triangle. So the legs will both be 6, and opposite the 90-degree angle, or the hypotenuse, is going to be 6 root 2. And then the other piece of information I know is time. So I know, sorry, not time. I can find time because I know the rate. I know that the rate P is traveling is 2 units per second. And remember, distance is rate times time. So if I want to find the time that P takes to go from B to C, well, that's that distance 12 divided by 2. So 6 seconds would be how long it takes for point P to go from B to C. And then to go from C to A, it's going to be 6 root 2 divided by 2, or 3 root 2 seconds. So that's my time. And there's going to be a different formula I'm going to use for the area when we're going from B to C versus C to A. So let's start by breaking up the two different pieces in terms of time. So it's going to be one formula when time is between 0 and 6 seconds. So again, when P is going from B to C. And then we're going to be, a new type of formula is going to be needed when P goes from C to A. So that is going to be when we're not greater than or equal to, just greater than 6, less than or equal to the total time, which is 6 plus 3 root 2 seconds. Okay, so let's start with the area of let's start with the first piece, how area is changing with time as P goes from B to C. Remember how area of a triangle is found? It's 1/2 base times height. Well, I know the base, so 1/2, 6 plus 6 root 3. Now the height. So how P, the distance here is changing with time, and how can I find how it is doing so? Well, it's rate, which is 2, times time, which we're just going to say is t. So that's how that distance is changing, which means if I want to find the height, given I'm in this 30, 60, 90 triangle, I'm just going to, opposite the 30-degree angle, it's just going to be 2t divided by 2, or t. So in this first formula, the area is simply that 1/2 base times the height of t. Well, things change when we now move to this going from C to A. So let's try to see what this area is going to look like. So we're going to have this type of triangle. Here's my point P now, and I'm looking for this area here. All right, so one nice thing is we still have 1/2. The base is still the same. It's the height that's going to be a little different here. So before I can find, again, I'm looking for this height here. And before I can find that, just like before, I want to find what this distance is. And it's not just simply going to be 2t, because remember, time is on a continuum. We're keeping on going up in time. So in order to figure out this distance here, well, I could think about what's the total distance on this piece here. So what's this distance here? And then subtract out that distance. So the total distance that we said before is 6 root 2. So I'm gonna write it actually over here because we're gonna have to divide by root 2 to get the, because it's a 45, 45, 90, to get this height, we'll divide by root 2. But so to get this distance here that I'm shading in blue, it's gonna be the total distance from A to C, which is 6 root 2, minus this distance here, the P to C, which is changing with relative to time. So it's going to be minus the rate. And how do I figure out, it's not just going to be T, because if T, for example, remember to get to C was 6 seconds. So what if I'm at 8 seconds? I'm not going to subtract 2 times 8, because this distance certainly is not reflected by that. I've actually got to subtract out the time associated with B to C. So I've got to say minus, again, the rate of 2, and then I'm going to say T, the actual time I'm at, minus 6. Again, I want to subtract out the piece that's not part of this leg. So that would be my distance here. And then to get the height, I'm just gonna, because it's a 45, 45, 90, I'm just gonna divide that by root 2. So that's one way to think about it. So we've got 6 root 2 minus 2, t minus 6, and then we're dividing that by root 2, again, to get the height. So another way to think about it is, simply, you could think about it in terms of time like this. Let me show you. So again, 1/2 base. And now in terms of figuring out, I'm still going to divide by root 2, but in terms of still figuring out this, I could say, okay, it's going to be the rate is 2. And then the time, in order to get the time just associated with this piece, it would be total time. So 6 plus 3 root 2 minus the time that was passed over here. So minus this piece again. So that's just another way to do it. You could instead do it in terms of, instead of doing just the total distance, minus rate times time of just that little piece, I could think about it doing the whole thing at once, saying, okay, let's figure out the rate is 2, and then to find the time associated only with this piece, it would be total time minus t. And then of course you'd have to divide by root 2 as well. So you could, again, that would be this 6, so this is or, that would be 6 plus 3 root 2 minus t, and don't forget times the rate of 2, but then you also have to divide by root 2. So these are challenging. It's just trying to think about how to represent, it's that second piece, because time's on a continuum here. We're keeping on going up, but you have to make sure that your length isn't being, or your distance isn't being misrepresented by that time. Okay, I'll give a couple more practice of these, but frankly, unlike previous years, we're not going to spend a ton of time on these, but they're fun application problems.